Now this system we've been working with does generate an EMF. It does create a current, and that current can be used to power stuff. But it's pretty impractical to use this as an actual source of power because, for obvious reasons, we can't have this rod keep going down a set of wires with a constant B field forever. Eventually it will run out of space in any setup we could use. So in practice, what happens is that you have a very strong magnet, and you can think of it as I guess a horseshoe magnet would work pretty well. You've got a north end here, you've got a south end here, and so there's a strong E field, or B field, sorry, pointing to the right in between those. And so we stick a loop that probably has lots of turns inside there. Pretend it looks more like a loop and less like I don't know what that looks like. And there is a constant magnetic field, but what happens is that this loop is twisted. It rotates. It rotates, and that rotation generates the changing flux. So we know that the EMF induced in the coil is minus N delta phi over T, and the delta phi turns out to be a sine wave. As the coil is rotated, the angle between the B field, and the coil keeps changing, and it's initially, like, if you think about it, the coil being perpendicular initially, that's the flux is related to the cosine of theta, but then the change in flux would be the derivative of that, which is a sine of theta. So we've got a minus N. Sorry, so our flux is B A cosine theta, where theta is the angle between the normal to the loop and the B field. So our d phi by dt, then, well, this theta is changing with time, and that's related to an angular velocity that we talked about that a lot way back in the day. It's a cosine omega t, and so then our d phi by dt, we get a minus that pops out of there. We got a minus b a omega sine omega t. All right, and so then we just stick that right in here for our d phi by dt, and the EMF we generate. The minuses cancel out, and so we get an EMF of NBA. Apparently it's a big basketball current loop. Ha ha ha. Alright. NBA omega sine omega t. That is the EMF generated now. This is a sine wave. So this is not like the currents that we've been talking about up until now. As t progresses, this will oscillate. The sine omega t will oscillate between -1 and 1, and this generates what is called an alternating current, because the current will change directions. It has a maximum of NBA omega, and then it'll go down to 0, and then it'll go to negative NBA omega. So the current will be flowing around one way, and then it'll kind of slow down and stop, and then current will flow the other direction, and so forth. Right? So let's just do a quick example calculation. Let's say that the coil in an electric generator, a generator is what this system is called when we're creating electrical power from a magnetic field. Probably should have said that to begin with. This is called an electric generator. The coil in an electric generator has 100 turns, has an area of 2.5 times 10 to the minus third meters squared. We want to supply a maximum current, so we're going to ignore the sine theta for the moment, or the sine theta. We want to supply a maximum current of 0.35 amps to a 12 ohm light bulb when the coil rotates at 60 cycles per second. What B field do we need? Well, first off, remember our omega is an angular velocity in radians per second, so 60 cycles per second. One cycle is 2 pi radians, so 60 cycles per second is 120 pi radians per second. So we need to know that. We also need to know what EMF we want. We can't find that directly from the information given, or we can't use just this equation. We need to know that we want this current, we want a 0.35 amp current to a 12 ohm light bulb. We know V equals IR, and so in this case our V is our EMF, and so the EMF we want is just equal to that current times R. And then from there, to find what B field we want, we can say IR equals NBA omega, and we don't want the sine omega t because we want that, because we said maximum current, and so we can make this sine omega t equal to 1, which is when we have the maximum current. So the B field is IR over nah, I don't want to do that. Get it? Nah means no. Okay. The current, 0.35 amps. Our resistance is 12 ohms. Number of turns, we have, where is the, 100 turns. We have an area of 2.5 times 10 to the minus third. And our omega is 120 pi. So if we stick that into our calculator, well, we got a 12 and a 120 and a 12, so we can make that a 10. And then that's 1,000 pi. And we've got a, okay, I'm going to stop canceling things out and just punch it into my calculator. And we get a B field of 0.04456, which is about 0.045 Tesla. Good, that's a reasonable number, unlike the last one. So that's just an example of how we can use this formula that relates to an electric generator to find a B field. So that's how an electric generator works. An electric motor works the opposite direction. So this generator is converting the mechanical energy of this rotating coil into electrical energy. Well, an electric motor takes electrical energy and converts it into mechanical energy. You know, motors are what power all sorts of things like cars and lots of other things. Yeah, and a motor is, in a sense, an electric generator in reverse. So we know that when there is a current going through the wire, that this current loop will experience a torque when put into a B field, and then the rotation, as the loop is torqued around, you know, the torque would reverse as the coil rotates around. However, there's an alternating current fed into the loop that is synced up with the rotation of the coil, so that torque produced is always in the same direction, and so that continues to generate mechanical power from the electric power. So a motor is kind of the reverse of a generator, which makes for a kind of interesting application. Some hybrid cars do this nowadays, that if you know there's a motor in the car, and this motor, or sorry, there's a motor in the car that causes the wheels to rotate. You know, the electrical energy that comes, you know, there's energy that comes out of the engine that goes into a battery, and then the energy from the battery is what drives the wheels to turn via an electric motor. But then some of that energy can be recaptured, because then when you want to brake, some cars utilize this when they're braking. Some of that kinetic energy from the wheels turning is then put back into the system, and then that motor takes some of that energy back in as electrical energy and throws it into the battery, instead of it just going into heat, which is what usually happens when you're braking. And then that energy, you know, comes back into electrical energy, and it makes the car more efficient. I thought that was a pretty cool, very intelligent usage of the relationship between a generator and a motor.